Good day, everybody. Welcome back to the first lesson on section properties. I've taken a nice warm-up example from if you were in my plant mechanics class early this semester or last semester. There's it over there. That is one of the exercises I gave you. I'm gonna start with this one over here, and of course those are the answers there. Bar x bar y, which I mentioned in the first lesson. And the question, there's the full question. For the following cross sections, calculate the position of the centroid. In the plant mechanics, we have to just do that bit over there, the first bullet point. Okay, and of course the position of the centroid is, that's the answers over there. Okay, but of course in TOS we're going to take that a lot further, and then after the position of the centroid, that means bar x bar y, determine the second moment of area by the x and y axis, or in symbol form it's ix and iyy. Then we need to determine the radius of gyration about the xx and the yx axis, or rxx and ryy. From the notes I gave you yesterday, you'll see where those symbols come from. And then the section modulus about the xx and y axis, or zxx and zyy. Okay, so let's work to that first bullet pointer and see if we get the correct answers. Alright people, I've drawn it out. Okay, there's the dimensions. And as you know, the first thing you need to do is to work around a particular point. Now when you get to this level in TOS, I don't tell you which point to work around. You choose a point and you work around that particular point. And as I said last in plant mechanics, always choose an extreme point. So I'm either going to choose that point, or I'm going to choose that point, or I'm going to choose that point. You can choose that one, you can choose that one, you can choose that one, but don't do that, because then it's adders, then you have to add and minus it, and it just gets confusing. Always choose an extreme point. I'm going to choose that point over there. Okay, so the first thing we do is we divide it up into shapes that we know. And people, when I talk about shapes that we know, if I just flick back to the table that I gave you sometime earlier, it will also be in your folder. I think it's over, there we go, shapes we know. Okay, so the shapes that we're going to be working with is the rectangle, the top one, okay, of those four there. So just by the way, make a note, we're going to look at the top one of those two sets of rectangles. Then there's triangles there, the top one there, that's the one we want. So that's the one that we must take note of, the top triangle of the four. Okay, and then of course the circle is a shape that we know. I want you to make a note of that one. And of course it's the semicircle there. Okay, so that's the four important shapes for us: top rectangle, top triangle, circle, and semicircle. Okay, so people, when I talk about shapes that we know, that's the shapes I'm referring to. So what we're going to do is we're going to divide that into the shapes we know. Right, I'm going to use that one there. Now people, I think some of you might have asked already, sir, but okay, let me first divide this one like so. And that's nasty, isn't it? You can either divide that rectangle like that and this one like this, or you can divide this rectangle into two like that there. So there's one there, there's one there, or you can either divide it into the long one vertically, the long one vertically, and that one like so there. Okay, now whether you divide it that way or this way, it does not matter. The only thing that's going to be different is the distances to the point you're working around, but ultimately you must get the same answer. So it doesn't matter how you divide it. Okay, right, and of course the centroid for this element is sitting in the middle over there. I'm going to draw it once for now, and it's sitting in the middle over for that one over there. Okay, I'm going to call that element 1, and I'm going to call that element 2. Okay, right. So, and I'm going to work about this point over there, okay, which is my point A in applied mechanics. I'm not going to name it anymore. Right, so, and as I said before, in applied mechanics, you can either use the table or you can use the formula and write it out as you want to. A lot of people like tables, but I find that they drop a table, they put in numbers, then they think, I must take that number, I must multiply that number, then I must divide it by this number, and I get the answer, and I write the answer in there. And then when they get the answer, they don't know what the answer is or what it means to them. Okay, right, so number A, let me do this over here. Right, so the first bullet point, okay, so I'm going to say bar Y. What's the formula? Bar Y, it's the sum of all the elements of the area times bar Y over the total area of the cross section. Okay, so I'm going to take element 1. What's its area? It is 20 by 150, 20 by 150 times, what's Y? Y is the distance from the centroid of the element to the point we're taking moments about. So it's the distance from there all the way down to there, which is 150 over 2. Why is it 150 over 2? Because from this table over here, the distance to bar Y there is D over 2. And what's D? D is the full depth of the section. That's why we do that, because that tells us to do so. So it's times 75 plus. Why plus? Because it's the sum of. Right, now be very careful, okay? Now, let me just do this, let me just do that. Okay, I'm going to just say that over there, because if you leave the 100 there, a lot of students say that element number 2 is 100 by 30, which is not going to be correct, okay? How far is it from there to there? It is 100 minus 20, so it is actually 80. Right, plus 80 multiplied by 30 times. And what's Y? Y is the distance from the centroid to the line we're taking moment areas about, which is 15. Why 15? Because from the table there, if D is 30, then the distance bar Y is D over 2. And that's why that's the case there. So it is 15. All over the total area of the cross section, which is 20 times 150, 20 times 150, plus 80 times 30. Right, you pick up a calculator, you stop the video, and you do the answer, and you check my answer against your one. Check me, and we must get the same answer. And what answer did you get? I got answer of 48.33, 48.33 millimeters. And if you leave that out, I take 1 mark off for it because I'm feeling in a good mood. Okay, it's a distance, and we're not making cakes. Okay, we're civil engineers. It's a linear distance, and all dimensions are in millimeters, so that's 48.33 millimeters. I'm flicking back to my answer. There we go, yippee. Okay, so that distance is the vertical distance from there up to the x axis, right? So, are you tuning in? This is where we get into the toss stuff. What does that mean? That there is the distance from the bottom there up to the x axis, and I'm going to draw it in on the sketch, and it's 48, so it's somewhere sitting over like so. Okay, and I'm going to call it xx and xx. Okay, right, so that is the distance from the bottom point there to the x axis of the whole cross section. Okay, so, and I'm going to draw it in. So I'm going to put it like so, and draw a line there, line there. So that there is 48.33. I'm going to leave the units of millimeters. Okay, but if the distance from the bottom to the x axis is 48.33 millimeters, then surely we can work out the distance from the x axis to, we call this here the topmost fiber of the cross section, and we call this here the bottommost fiber. Here's the word fiber. Fiber. Like, fiber as in fiber. Wi-Fi fiber. There's it over there. Okay. Bottommost, that means a thin sliver of it. So the distance from the bottommost fibers to the x-axis is 48.33. And then from the geometry of the section, we are able to work out the distance from the x-axis to the topmost fibers. Okay, and what will that be? That will be 150 minus the distance we just found. So it's 150 minus 48.33. 48.33 is equal to is 101.67. Let me throw the arrow in here. It is 101. Is 101.67 millimeters. Okay, and people there's names for that. Okay, that distance there, we call it y top, and that distance there, we call it y bottom. Okay, and what's y top, y bottom? Y top is the distance from the x-axis to the topmost fibers of the cross section, and y bottom is the distance from the x-axis to the bottommost fibers of the section. Okay, so y bottom plus y top is equal to the full depth of the section. Did you see the word depth there? Okay, the distance from there to there, we do not call it the height. We do not call it the height. If you go to the doctor and they say, what's your height, sir? They put you on the floor there, and they measure your distance from the bottom of your feet to the top of your head, and they say, sir, madam, that's your height. This is not height. This is the depth of the section, how deep the section is. Right? So y top plus y bottom is equal to the full depth of the section. Right? Have we finished calculating the position of the centroid? No. We need to still work out bar x, that is how far it is from there to there. Okay, and what we're going to do is we are actually going to work out what we're going to do now, people, we're actually going to work out the distance from there. Ach man, and people, what we're actually going to do now, because we're working about this pointer, we chose to work about at this point, we're going to work out the distance from there to there. Okay, and as I said in applied mechanics, where these two axes intersect each other, that is the position of the centroid there. Sometimes it's also called capital G for center of gravity. Okay, so we're going to do the famous bar x, right? So let's do that. So bar x is equal to, before I do that, right, people, and the formula there is, of course, and I just clean it up a little bit here, is bar x. So bar x is equal to the sum of all the area of the elements times x, horizontal distance, over the total area. Okay, right, element number 1, 20 by 150, which is the area, 20 times 150 multiplied by x. What's x? X is the horizontal distance from the centroid of the element to that line we're taking moments about. We're taking moments about there. Remember we said moments of areas, which is half of 20, which is 10, plus area of element number 2, 30 times 80, or 80 times 30, doesn't matter, 80 times 30, times x. What's x? X is the distance from the centroid of the element all the way, notice all the way, not from there to there, all the way from there to the line we taken moment about. So from there to there is 80 over 2, which is 40, plus 20, so it's 60. Okay, now if you're going to make that 40 there, that is going to be wrong. Over the total area of the section there, okay, which I think I worked out, so let me just dig it out again. Yep, the total area I got from the previous one there, which is all over that. Okay, Just all of that there, which is 5400. 5400 is equal to, right, so you stop the video and you work at it and you check your answer against my answer. And I got 32.22 millimeters. 32.22 millimeters. Okay. If you leave it the millimeters, I take off a mark because it's a straight linear distance and all dimensions in millimeters, right? I'm going to flick back to the answer sheet or that exercise I gave you earlier, okay? And there's the answer, okay? 32.22 millimeters. So what is that? That is, because we worked from this point this away, okay? That means that distance there is 32.22 millimeters, okay? And if the distance, we call this here the leftmost fiber of the section. So if the distance from the leftmost fiber, distance, and that's the distance from there to the y-axis, then surely we can work out the distance, okay, from the y-axis to the rightmost fiber of that over there, like so. It's a bit sloppy, but anyway. My y-axis there. So if the distance from there to there is 32.22, then surely the distance from the y-axis to the rightmost fiber is equal to 100 minus 32.22, which I'm going to do now. And I get 67.78 millimeters. 67.78 millimeters. Okay. And that distance there, okay, now more specifically, we're going to call that distance there is called x left, and that's going to be called x right. Okay. So people, so from this point onwards, we're not going to call it bar x bar y anymore. I'm going to call that's going to be called y bottom. That's going to be called x left. Okay. So y bottom is the distance from that point up to the x axis, and y top is the distance from the x axis to the topmost fiber. X left is the distance from the y axis to the leftmost fiber, and x right is the distance from the y axis to the rightmost fiber. Okay, so people, if I flash back to the question there, we've determined the position of the centroid. Okay, so that's how we do that over there. Okay, so people, I'm gonna now continue with the next part of the question, calculating the second moment of area about the x and y axis. Right, people, the second point we want to work at there, the second part of the question is calculate the second moment of area about the x and the y axis over there. Right, the formula. I'm casting my mind back to the formula there. There's the formula from the notes I gave you. Okay, it says either that or that. I'm going to use this one here, and we're going to work out the second moment of area about the x axis and the y axis using the parallel axis theorem. Right, I'm going to state it like so. So I x is equal to the sum, and there's a square bracket there, and I said yesterday, notice small x, it's not the same thing. I'll explain it as I do that, plus a times h squared. Okay, so we're now going to calculate the second moment of area about the x axis. That's the x axis there. Right, now if I just go back, if you cast your mind back, that there is the x. This drawing is going to get very full. Right there. Okay. This here is the x axis. of element 2, and that there is the y-axis of element 2. This here is the x-axis of element 1, and this here is the y-axis of element 1. Can you see big X, small x? Can you see small y, big Y? And that's it over there. This x is the x-axis of the whole cross-section, and this x is the axis of each element. Okay, so we've got two sets of x and y axes, and we've got one set of big x and y axis. That's not small, that's capital, and that's not capital, that's small. Get it right, because they don't mean the same thing. Okay, that's why we do that. Right, people, so there's the formula, and the formula, we're going to use the parallel axis theorem to be able to work out the x and the second moment of area about the x and y axis. Now, yesterday, I did say I'm going to talk about the second moment of area. There's a little note there. I'm going to refer to that note now. Right, people, I just want to talk about what second moment of area is all about. Now, if you just look at it there, you'll see it is measured in either millimeters to the power 4 or centimeters to the power 4. Now, if we measure something in a straight line, it's millimeters. If we find the area, it's millimeters squared, because we're multiplying a length by length. And if it's millimeters to the cubed, it's volume, because we're multiplying a length times a width times a height. But this is millimeters or centimeters to the fourth. It is a concept. It is something that you can't see or touch. It's a design concept. Okay. So anything, any straight distance to the power 4 is second moment of area. And here's just a little note about it. Okay. Second moment of area. The second moment of area, or SMOA, can be understood to be, I'm just reading the document, a measure. It's a measure of the resistance of a beam to deformation under loading. Now, a beam is supported at its ends, and it's got a load at the top there, so it wants to bend, sometimes also called the I value. The bigger the second moment of area of a section, the higher is its resistance to deformation under loading, and vice versa. Once you get to learn to calculate the I values of various sections, which we are going to do now, compare them with each other and see how and why they are placed the way they are in the structure. For example, consider the first beam in the list of the two beams below. There's two beams in the table there. Okay, the one is called a 305 by 102 by 33. Okay, I'll explain this as we go along later. And the other one is a 305 by 127 by 37. There's the note. For example, consider the first beam in the list of two beams below. That is the 304 by 102 by 33. There's it over there. Okay. It has an IXX value of 6501 centimeters to the fourth. Okay. And the one below it has a value of 7171 centimeters to the fourth. Okay. What does it mean structurally? It means that the beam is placed vertically. That means with its XX axis horizontally, as you can see there. And it is placed this way in the structure because it is stronger, so-called stronger, to resist bending about the XX axis, and weaker to resist bending about the YY axis. So if you compare that value there and that value there, you'll see that's bigger and smaller. So that means the beam is stronger about the XX axis and weaker about the YY axis. That means the beam is placed like this, so-called vertically, so the loads are acting on it vertically from there down in that particular way and not the other way. Okay. So if you look at the beam, the next beam below, the 305 by 127 by 37, it has an IXX value of 7174 cubic centimeters, meaning that this beam is more resistant to bending about its XX axis compared to the one above it. Okay, so this beam here is stronger than this one. And stronger means, when you say stronger, that we mean it resists bending greater about the XX axis and that one over there. So generally, the bigger the beams in the table, the deeper they are, the stronger they are, that means they can resist bending more. Okay, so what does the I value mean? The I value mean actually is a measure of how much a beam can resist deformation or bending under loading. Okay, so we want to place a beam in such a way so that the bending takes place about the axis with the bigger I value. Okay, so that's what second moment of area is all about. Right, I'm going back to my calculation over here. Right, so there we go. Let's do the calculation. Is equal to, right, sum of, right, I'm just putting a little one there to say that I'm dealing with element number 1. Right, what's Ixx? Ixx is second moment of area. Right, I'm going back to my table. I'm going to back to my table there. Sorry. What shape do we have? We have a rectangle. That there is calling for the second moment of area of a rectangular section. And what's the formula for the area of a rectangular section? I go back to my table, and there we go. Okay, so the second moment of area of a rectangle is b d cubed over 12. What's b? B is the side there, and b is always a side parallel to the axis we are taking second moment of area about. So that's b, and that's d. So Ixx for the rectangle is b d cubed over 12. Right, what's b? B is 20. What's d? D is 150. You've got to remember that, people. Okay, you've got to remember those formula for those various sections there. So for the rectangle, it is b times 150 cubed over 12 plus A is for area. What's the area? 20 times 150, like we know it. 20 times 150 times h squared. Right. People, are you tuning in? This is where students just struggle. Okay. H, are you listening to me carefully? H is the distance from the centroid of the element to the centroid of the whole cross section. It is this distance over here. Did you get that? H is the distance from the centroid of the element to the centroid of the whole cross section. Can we work at it? Yes, we can. We can work at it because we worked at y top. Okay, so can we work at the distance from that axis to that axis? Yes, it is y top minus. Okay, how far is it from there to there? It's d over 2. From there to there is 150 over 2. So 101.67 minus 75 is equal to h there for that section. Okay, so I'm going to do the calculation, and you do the calculation too, and you check my answer there. 101.67 minus 75, and it is equal to 26.67. 26.67, and it's squared. Close it and square bracket, and plus. Why plus? Because it's the sum of, right? And I do exactly the same thing for element number 2. Second moment of area for the rectangle is bd cubed over 12 from the table I gave you. What's b? What's d? B is always the side parallel to the axis we take in second moment of area band. So b is not 30. B is not 30, people. B is 80. Okay? A lot of people say it's the smaller side. It's not the smaller side. It's the side parallel to the axis we take in second moment of areas about. So it's 80 times 30 cubed over 12. Plus the area, which is 30 times 80 times h. What's h? Are you tuning in? H is the distance from the centroid of the element to the centroid of the whole cross section. Did you get that? H is the distance from the centroid of the element to the centroid of the whole cross section. Can we work at it? Yes, we can. And we can work at it because we worked at y bottom in the previous in the previous section there. So it's y bottom, which is 48.33 minus, how far is it from there to there? Minus 15. So it's 48.33, take away 15, and it's equal to 33.33. So it's 33.33 squared, y squared, because the formula says so. Close the round bracket, close the square bracket, and you get the answer. Now people, you can see here, there's lots of room to make mistakes. Get it right. Okay, do your calculation and only proceed with the video until your answer is exactly the same as mine. Okay people, did you get your answer? Well, I got my answer as, and it's going to be a big number. It's going to be a big number, as you know. I got 10, 605, what's the units? Millimeters to the fourth. Leave that there, I take a mark over that. Or, if you're depending on the make of a calculator, or if you want to, you can write it in scientific notation. What scientific notation? A number followed by the decimal. Okay, so it would be 1.06 times 10 to the power 7 millimeters to the fourth. Okay, that's the correct answer. That is also a correct answer. It's one or the other. So there's full decimal notation, that's scientific notation. Okay people, so that there is the second moment of area about the x axis. You can see there that there is quite a lot. Okay, and we are only halfway by the second bullet point there. We still need to work out the second moment of area about the y axis, or IYY, which is what we're going to do right now. Okay, right, so let's work at IYY. Right, IYY, the formula is very similar. IYY, notice capital Y is equal to the sum of second moment of area, small y, same thing, okay, plus A times H squared. Okay, we're using the parallel axis theorem to determine the second moment of area about the y axis. That big Y is that Y there, that little y there is that one there, and that one there. Get it right. Okay, right, there we go. Same thing, but we're going to work about the y axis. Right, I'm doing element number 1. What's the formula for the second moment of area of a rectangle? If I go to my table there, what happened here? Oh, it didn't. Okay, something with my piece here. Okay, but it is BD cubed over 12. Okay. Right, there's it over there again. I just pulled it up. Okay, it's BD cubed over 12. But remember, B is always a side parallel to the axis we are taking moments about. Okay, so B is now 150 and D is 20 for element 1. Did you get that? It's 150 times 20 cubed over 12. Plus A for area, which is 20 times 150, which we know by now almost out of our heads, times H. Are you listening? Okay. What's H? H is the distance from the centroid of the element to the line we take in moment of area about. Sorry, that's nonsense. I'll say that again. H is the distance from the centroid of the element to the centroid of the whole cross section. I'll say that again. H is the distance from the centroid of the element to the centroid of the whole cross section. Can we work at that? Yes, we can, because we have to work at X left from the previous bullet point there. So it will be 32.22 minus 10, because from there to there's 10. So 32.2 minus 10, it is 22.22. 22.22 squared. Formula says so. Close the round bracket, close the square bracket, and plus y plus, because it's the sum of. And I'm going to do the same for element number 2. It's BD, the second moment of area for the rectangle is BD cubed over 12. What's B? What's D? B is a side parallel to the axis we take in second moment of area about. So it's 30 times 80 cubed. 30 times 80 cubed over 12. A bit skew there. Plus A for area, which is 30 times 80. Times H. What's H? H is the distance from the centroid of the element to the centroid of the whole cross-section. H is the distance from the centroid of the element to the centroid of the whole cross-section. Can we work with it? Yes, we can. It is X, right? Which is 67.78 minus the distance from there to there. And how far is from there to there? It's 80 over 2, which is 40. So 67.78. So 67.78. Take away 40 is equal to 27.78. 27.78 squared. From the formula, close bracket, close the square bracket, is equal to, right, long calculation, lots of room to make errors, but stop the video, do the calculation, and check that your answer is the same like my answer before you proceed. Okay, I'm going to work at my answer now. And the answer I get is 4713. Let's see, 4713, 333, 333. Oh, lots of threes. Maybe let's play the lotto. I'm only joking. Millimeters to the fourth. Okay, and if I write that in scientific notation, which makes it a bit easier, I get 4.71 times 10 to the power 6 millimeters to the fourth. Okay, people, that's the end of the second part of the second question. Okay, we've now worked out our XX and IYY. Now, people, up to there so far, you can see that's a lot of numbers to write. Okay, lots of room for error. Okay, but once you get to this part of the question successfully, the worst is over. From here, I'm just using values that we know, as I said in my talk yesterday in the introduction. Okay, now, people, if I just very quickly look at IXX and IYY, we say that IXX, if I just record it again here, IXX, okay, IXX was equal to 1.06 times 10 to the power 7 millimeters to the fourth. And if you leave it the units, I take a marker for that. Okay, so notice say for this section, IXX is 1.07 times 10 to the power 7 millimeters to the fourth, and IYY is 4.71 times 10 to the power 6 millimeters to the fourth. Now, if you compare that value with that value, which is the larger one of the two, that's the larger one of the two. So what does it mean? That means that this beam is stronger about the XX axis to resist bending. Okay, so if we use this L shape as a beam, we'll actually put it like this and load it with the loads from the top down with the support at its ends. Okay, so that is how we work at the IXX and the IYY for a particular section. People, that's the end of that second part of the question. I'm going to do the next two. I'm going to do the next two in part B of another video. Otherwise, this video is just going to get too big, maybe to download or to watch. Okay, so I'm going to do radius of gyration and section modulus in the next half of the next video. Okay, I'll see you in the next lesson for those two there.